So today we'll discuss quantum machine learning. Now, before going into quantum machine learning, let's start with the traditional machine learning concept. In classical machine learning has achieved remarkable success in different application areas. For instance, in image classification tasks, machine learning tasks, in healthcare AI applications such as medical diagnosis or prognosis tasks. And it has recently become a cornerstone of modern technology, enabling decision-making across diverse fields. Now, we have different paradigms in machine learning. For instance, we have supervised learning, unsupervised learning, reinforcement learning. There are different algorithms that we have. Some of the popular algorithms are like support vector machine classifier, convolutional neural networks, etc. Now, these algorithms actually basically try to learn patterns from the data, complex patterns from the data. For instance, if I have an image, we can train a machine learning model, deep learning model actually, to learn to recognize a cat from the image. Now, these models, these machine learning models actually operate in classical computers, that is actually using binary bits, 0 and 1. And we have conventional memory and processing architectures like CPU or GPU. Now, modern machine learning techniques have achieved remarkable performance using such classical computers. Like we have GPU for deep learning, and they actually support faster processing. So this has actually paved the way for enormous application areas in different data-driven application tasks. Now, when it comes to quantum machine learning, well, this is not just about new versus old, not like that. Quantum machine learning is actually a completely different way of representing and processing information. Now, the original idea behind QML, quantum machine learning QML, was to investigate whether quantum computing can help to improve the performance of machine learning algorithms by making the algorithms much more efficient, faster computation, or like creating or developing completely new set of algorithms using quantum theory. Now, when it comes to quantum computing, okay, it's a completely different paradigm of computation. So in classical computing, we have binary bits like 0 and 1. In quantum computing, we have quantum bits, in short, qubits. So classical bits actually can exist on either 0 or 1 at a given time, 0 or 1. But in qubits, when it comes to qubits, they can actually exist in a state of superposition, representing both 0 and 1 simultaneously. Okay. So there are other phenomena other than superposition, for instance, entanglement, interference. We'll talk about these things a little bit later. So these phenomena altogether actually provides computational speedups for certain different problems. Okay. So this allows for information processing in ways that is not possible in classical hardware. Now, quantum machine learning tries to combine quantum computing, the ideas from quantum computing with machine learning to process the data in a fundamentally different ways. Okay, they actually reference phenomena like superposition and entanglement. Okay, and try to address the computational bottlenecks of high-dimensional data and different problems like combinatorial problems. Okay, now QML is still in its infancy. Okay, it is not something that has been established properly yet. It is primarily characterized as a theoretical field. It is facing severe limitations, especially hardware limitations. We look into it gradually one by one. Now, some of the quantum phenomena, for instance, superposition. So if we think of it like, I think of like a coin, if we flip it, when we flip it, it is like head or tail. We cannot say which one it is. Only when we pick it, only when we pick into it, or it actually comes into the ground, we can understand whether it is 0 or 1. So this is like the concept of superposition, that a qubit can simultaneously encode multiple possibilities. Okay, it collapses into one definite state only when it is measured. So this allows for quantum circuits to evaluate multiple states at once. So it enables parallel exploration, like going through different paths in a maze at the same time. Another phenomena is entanglement, that is, two or more qubits become linked. Okay. So if one state changes, it instantly influences the other state as well. So these states are correlated. That is not possible in classical computers. So these concepts are utilized in many different ways. Okay. For instance, capturing correlations between features like this. So we have superposition, single qubit existing in multiple states, and these qubits can be linked, two or more qubits can be linked, that is entanglement. Is a very simple example like fraud detection. In a fraud detection task, like in an ATM booth, we want to detect fraudulent transactions. Now, in classical machine learning, we use different features. Features like transaction time, when the transaction is being made, or in which location. Some of the locations can be far away, let's say far away from the city, that can be a little bit dangerous. Or for instance, time. If it is the midnight, there is a good chance that it can be a fraudulent transactions like this. Or let's say multiple mismatched pins, okay, has been used. So in quantum machine learning, what can be done that these features can be encoded into a qubit, okay, then they can be entangled so that correlations are represented, like large amount, unusual locations, they are really represented in a quantum state. Then this quantum states can represent correlations very compactly, and it can actually make it easier to spot fraud signatures. Gotcha. Now, let's see the differences, some of the differences. For instance, in core computational paradigm, in classical ML, we have binary bits, that is 0 and 1. So the computation is totally deterministic. And we use standard hardware like CPU. For deep learning, we use GPU. Now we have TPU, tensor processing unit, and they processes one state at a time. But in quantum ML, it is based on qubits, that is 0 and 1 or superposition of both different phenomena that we have, and they are run on quantum computers. And they process, and it processes many states simultaneously. Now, when it comes to information representation, in classical ML, data is represented as like vectors or metrics, or in some cases tensors. For instance, in an image, it is represented like a set of pixel values in a matrix. Although it is unstructured data, but like this way is a matrix. In a structured data, we have a CSV file like this way. But in quantum machine learning, it cannot work with this kind of data. The data has to be encoded into quantum states. This requires feature encoding. We'll discuss about it a little bit later. And this is one of the primary bottlenecks of quantum machine learning. That's right. Now, in classical machine learning, every input, that is like every sample, is represented as a feature vector. So the data that we have. So the whole data can be represented as a n by m matrix, where n is the number of samples and m is the number of features. Then it can be directly fed into the machine learning model. In some specific algorithm, for some specific algorithms like support vector machine, we can also use a trick that is called kernel trick. Okay, that is, the data can be like map into a higher dimensional space. Okay, that allows to make them separate, make the data linearly separable for different classes. Okay. So this concept is utilized in support vector machine classifier. And this is all this, a version of this one is also applicable for quantum machine learning as well. Now in QML, data needs to be represented as quantum states. This is called a Hilbert space. So a n-qubit quantum state resides in a complex vector. Quantum states are in complex vector, represented as complex vector in a dimension of 2 to the power n. So that's like a huge representational capacity. So with just 10 qubits, we have 1024 dimensional space. Okay, so this is something that has been an advantage of QML, and this is one of the things that is utilized in QML. Okay. In contrast, in classical ML, the features are limited by practical dimensionality. We have the problem of high dimensional problems. Now, when it comes to data handling, okay, now classical ML, they actually work naturally with classical data sets, and there is no transformation actually needed. Unlike NLP, in NLP, we have to vectorize it, so that's a different thing. But in quantum machine learning, it requires quantum encoding. Okay, the classical data cannot be used directly. It requires quantum encoding. So what is a quantum encoding? Now, quantum algorithms cannot directly use classical data sets. So the data must be encoded into quantum states. And there are several ways. These are some of the ways. For instance, basis encoding using quantum basis states, or amplitude encoding using the amplitude vector of the quantum state, or angle encoding, or Hamiltonian encoding. Okay, I'm not discussing in details of these things here in this lecture. It will be in the next part. So in classical machine learning, we have directly reading or feeding data. In QML, we have to encode. And when you encode, this process becomes resource intensive. Okay. And the quality of encoding also influences the model performance. Now, the models that you have in classical machine learning, we have some of the models like linear models. For deep learning, we have CNN, RNN, transformers, etc. Now, there are some investigation into quantum machine learning. Several new algorithms has actually come out. For instance, for SVM, we have kernel trick. In quantum ML, QML, we have quantum kernel methods, QSVM. Then you have quantum version of the neural networks, like a hybrid technique. Then quantum PCA. A more recent one is parameterized quantum circuits or PQC. We'll discuss this in the next lecture. The training process in classical machine learning is very straightforward. We have gradient descent algorithms, we have backpropagation, then fully differentiable pipelines. Quantum ML, however, uses a hybrid approach. Quantum circuit is used for forward pass, then classical optimizer is used for parameter update rule. Not the entire training process is done using quantum hardware. No, not like that. Part of it. Now, in classical machine learning, the system that we have right now is quite established, quite matured, like we have PyTorch, TensorFlow, frameworks like that. This is widely deployed and very much scalable. It can work with huge data set. Okay. Now, quantum ML actually limited, quite limited by current hardware. There does not exist a mature ecosystem like that as of yet. And the current devices have some problems like noisy operations. They have limited qubit counts, and a major problem is decoherence. So that actually limits the applicability of QML techniques. So what is decoherence? So a quantum system loses its quantum properties, that is like superposition properties, when it interacts with the surrounding environment, like stray atoms or electromagnetic fields. So whenever it interacts, it loses the information and causes the particle to get into a single state. Okay, not in a superposition, but to a classical single state. This is one of the main cause of computational errors in quantum computers, and this needs to be eradicated or limited. Okay, that necessitates extreme isolation and cooling. So this is one of the major problem of the current hardware, quantum hardwares. So that comes a question like, where can QML actually offer an advantage over classical machine learning? আচ্ছা, now, QML does not actually guarantee a complete universal improvement over classical ML. It is not like that. There are specific settings or specific areas where quantum machine learning can actually provide some advantage. For instance, high dimensional data representation. Due to the Hilbert space that we talked about earlier, that is actually one of the key areas where QML can actually provide major advantage. Then complex optimization tasks, it has been already used. Quantum computing has been already used for this type of applications. Then different tasks where it is natural, where quantum mechanics is naturally aligned with the data. For instance, in material science, in quantum chemistry or physics, some of the recent papers are actually there are some recent papers on quantum machine learning and generative modeling in different applications like healthcare applications. This is actually coming up recently. So this is actually an active research area. Now, quantum machine learning is most promising in quantum native domains like physics or chemistry. But for machine learning tasks like mainstream machine learning tasks like pattern recognition tasks, image recognition tasks, in NLP tasks. Okay, so for those part, classical machine learning actually is still the best that we have because properly optimized classical machine learning models clearly outperforms QML. And QML, one of the major limitation of the QML is hardware constraints. Okay, so what are those hardware constraints? So for instance, qubit count. Now, current quantum computers that you have only have tens to a few hundreds of qubits, far below that we need for machine learning tasks, large-scale machine learning tasks. Now, as for these qubits, they are not fault tolerant. Now, to get the speed up, the exponential speed up that is promised by theoretical QML, that does not exist yet as of in practical scenario. Okay. Now, these qubits are also extremely fragile. They lose information quickly due to decoherence that we mentioned earlier, so any contact with the environment. So noise actually leads to error in computation, making the training process quite unstable. Now, error correction is possible, but that requires even more qubits. making it much more complex, much more complicated. So there are no clear quantum advantage that has been demonstrated for most of the machine learning tasks, like the traditional machine learning tasks. There are certain application areas where QML is actually very promising. QML looks very promising, but it is still in the research phase. It is not yet in the deployment phase. So the key takeaways that we have from this lecture that we have, QML introduces a completely new computational paradigm based on quantum mechanics. This is quite promising for high dimensional optimization problems or different quantum native domains. Okay. The current systems are quite limited by hardware constraints. Okay. Now, QML is definitely not a replacement for classical ML, but it is an emerging paradigm, and that might look very promising in the future, depending on what is the outcome. Thank you.